Let us try to calculate the work done in any thermodynamic process. Now, for that, let us take that we have a cylinder that has a movable piston and 1 mole of ideal gas. Now, the movable piston has a cross-sectional area of A, and due to the application of pressure P, it has moved across a small distance of dx. Now, since it has 1 mole of ideal gas and due to the application of pressure P, there was also a certain force exerted on the ideal gas. And due to the application of that force, it has crossed a distance of dx, and therefore work has most certainly been done in this process. Now, by definition of work done, we know that work done dW, we consider the work done to be very small. dW is equal to F and dx having their dot products. Now, since the direction of F is along the direction of P and dx is also along this direction, so we can say that the dot product is df dx cosine of 0, which brings us to the fact that f dx is basically the small amount of work done. Alright, now as for calculating f to proceed this thing, we know that P, pressure, is equal to force over area, or from this given scenario we can say that F is equal to what? P times A. Therefore over here we can say that dW is equal to what? P A dx. Now, what does this term A times dx represent? Well, A times dx represents that the change in volume from bringing this movable piston from this to this along dx is basically the change in volume A times dx, and we can represent this A times dx as P dV, which means that the change in volume occurred by the work done is basically what? dV. Alright, so we have that dW is equal to P dV. Now, in order to calculate the entire work done, we take the antiderivative, which is work done is equal to the antiderivative of P dV, and thus we have the entire work done in a thermodynamic process, which is the antiderivative of P dV. Now we know that we have 4 types of thermodynamic processes, which are isobaric, isochoric, adiabatic, and isothermal process. We are now here to calculate the entire work done in any thermodynamic process: isobaric, isochoric, adiabatic, and isothermal. So let us proceed with the calculation of the work done in each and every single one of those thermodynamic processes. We know that in an isobaric process, the pressure of the system remains constant. So we can say that the work done, W, is equal to the antiderivative of P dV, happens to be this, since P is constant. And if we take the antiderivative of dV over here, we are left with the fact that work done in an isobaric process is PV. Now let us look at the graph of P versus V for an isobaric process. Here, the y-axis represents pressure and the x-axis represents volume. Since the pressure is always constant and volume changes, so we can say that the graph looks like a straight line. A straight line along the x-axis or along the axis that represents volume. Alright, moving on with isochoric process. Now, in an isochoric process, we know that the volume remains constant. And if the volume is constant, we have that work done W is equal to the integration of P dV. And since volume itself is constant, so we can say that the entire work done is basically zero, since there is no change in volume over here. So we can say that the work done in an isochoric process is basically zero. Now, if we look at the graph of P versus V, we can say that the graph is basically a perpendicular line along the axis that represents volume. And there is no net work done in isochoric process. Moving on with isothermal process. Well, in an isothermal process, we know that the temperature remains constant. Now, if the temperature is constant, we can say over here that the work done is equal to the integration of P dV. Now, we know from the ideal gas equation that PV is equal to what? nRT. And if we represent P in terms of the other variables, we can say that P is equal to what? nRT over V. So we plug this thing into this equation and we get that work done is basically the antiderivative of what? nRT over V times dV. Since volume is not constant over here and the other things, which is N, R and T, is constant, we can just pull that thing outside as a constant like this, and we can say that it is dV over V and its antiderivative. And from the basics of integration, we know that this is basically nRT ln of final volume Vf over initial volume Vi. Let me write this down over here. Now, let us look at the graph of an isothermal process. Let me erase this. Well, the graph of an isothermal process is kind of like a slope that looks like a curve of this particular nature. Alright, so the only work done that we are left to calculate is that in an adiabatic process. But for that, we need to understand the concept of heat capacity at constant pressure, constant volume, and from that we need to understand what the ratio of them is, and we denote that by gamma. So that will be left for our next lecture. Well, that's all for today.